The Doppler effect section of the physics paper starts with question 1.6 of multiple choice, which reads, the siren of a police car moving in front of a truck emits a sound of frequency F. Both vehicles are traveling at the same constant velocity. The frequency of the sound heard by the driver of the truck is. And what's important here is that both vehicles are traveling at the same constant velocity. What that means is that there's no relative motion between them, which we know is the only time when the Doppler effect applies. So since there's no relative motion between them, the truck driver will hear exactly the same frequency that is being emitted, and therefore the correct answer to 1.6 is A. Question 6 reads, the siren of a train moving at a constant speed along a straight horizontal track emits the sound with this constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are shown below. Question 6.1, state the Doppler effect in words, and the definition as given in the guideline document is the apparent or perceived change in frequency as a result of the relative motion between the source and the observer. Question 6.2, does the detector record the frequency of 3,148 hertz when the train moves towards or away from the detector? And what we should hopefully see is that the detector, if this is in the middle of the motion of the train, at some point when the train is approaching, the waves are going to bunch up before reaching the detector, which means that as the train approaches, the frequency will be perceived higher. And then as the train moves away, those waves will then spread out and the frequency will be perceived lower. So they're asking what the motion of the train is when the frequency is perceived higher in the motion. At that point for question 6.2, because the frequency is perceived higher, the train must be moving towards the detector. Question 6.3, calculate the speed of the train, take the speed of sound in air as 340 meters per second. And so we would always start off, we can see that the Doppler effect is going to be applied here. And so we always start off with the formula as it is given. The observed frequency is equal to the speed of sound in air plus or minus the speed of the observer over the speed of sound in air plus or minus the speed of the source, and that is multiplied by the frequency of the source. Now, what we can hopefully see is that there are actually two motions here. There's one when the train is approaching the detector, and there's another motion when the train is moving away from the detector. What that means is that the Doppler effect is actually going to be applied twice here. Once for when the train is moving towards the detector, and the second time when it is moving away from the detector. And so we're going to write two separate Doppler effect equations. The first one is when it is moving towards, the perceived frequency is 3,148. The speed of sound in air is given to us as 340 meters per second, and the detector is stationary, therefore its velocity is 0, and the train is moving towards the detector, and therefore we subtract the speed of the source, and then the frequency of the source is unknown. So here we can see we have an equation. Unfortunately, there are two unknowns, but what we do have is enough information to write a second equation for when the train is moving away from the source. And when it is moving away, the observed frequency is 2,073 hertz. The speed of sound in air is still 340. The detector is still stationary. Therefore, this is 0. Over here, you do not have to write in plus or minus 0, but you can if you want to. And then we can now say the train is moving away, the source is moving away, so therefore we add the velocity of the source in the denominator, once again multiplied by the frequency of the source. What we now have is we have two equations and two unknowns where the speed of the train Vs remains the same. So those are equal, as do the frequencies of both sources, because the sound emitted by that train does not change. So we would have to rearrange this, we would rearrange it so that the frequency of the source is equal to 3,148 multiplied by 340 minus Vs divided by 340. And we would rewrite the equation over here as the frequency of the source is here equal to 2,073 multiplied by 340 plus Vs divided by 340. And now we can say, since this train is emitting the same frequency, it's the same thing, we can say these two must be equal to each other. 3,148 multiplied by 340 minus Vs must be equal to 2,073 multiplied by 340 plus Vs, and then therefore we can solve for the speed of our source to find that the train is traveling at 70 meters per second. Question 6.4. reads, the detector started recording the frequency of the moving train's siren when the train was 350 meters away. Calculate the time t1 indicated on the graph above. And this time t1 refers to the time when the train is at the detector, because we can see at that point it goes from traveling towards the detector to traveling away from the detector. So essentially the question is asking, how long did it take this train to travel 350 meters? So we could start out with a very simple calculation where we just say that delta t is equal to delta x over the velocity. We could also have used an equation of motion, but either way we get to the answer where we say 350 divided by 70 meters per second, and the answer there is then 5 seconds. The way that this question is marked, once again, the underlined parts of this definition are the words that must appear in the definition to have all the marks awarded. Question 6.2 is very simply just 1 mark for correctly saying that the train is moving towards the observer. Question 6.3, 1 mark for starting out with a formula as given in the formula sheet. And then for each of the separate expressions, you get 1 mark for correct substitution on both sides. And what's useful, or what's nice to see here, is that for reaching this point, for reaching the point where we've just done the substitution, the mark is already 5 out of 6. So the remaining part of this question 6.3 is largely just algebra, where you are rearranging, and for that you only get that last mark. So if you do struggle with these kind of rearrangements, that is not something to be concerned about, because you can still get 5 out of 6 for getting to this point over here. And then finally, question 6.4, there's 1 mark for just some kind of showing a calculation, showing that you understand that it's essentially the distance divided by the time, and not just jumping straight into the correct answer. Please remember that all of your answers must have the correct units.